This example is solar system, and it is a 39-bus IEEE system set up to automate some contingency cases for 300 megawatt IBR at bus 14. So we've added some components. There is a meter for each of the three lines coming out of bus 14. I've inserted a breaker at each end of each of the lines coming out of bus 14. And there's a fault location. So let's see. This fault loc with the blue node there, that is like an electrical jumper or electrical page connector. So fault loc 1 corresponds to this instance of fault loc 1 over here. And so it's a way to organize the timed fault logic and the breaker logic all in one place. So my array of faults with fault location 1 is on this line from bus 14 to bus 15, and the breakers at each end of that line are breaker 1 and breaker 2. So I can organize, the stack of 3 includes the fault and the 2 breakers, and then the same with the fault on the second line and the third line. I want some measurements, so I'm right here. I'm calculating the real and reactive power, the RMS voltage coming out of the plant, and then I'm also getting a bus voltage. These are instantaneous bus voltages at bus 14. So these meters should stay in service even when the line breaker is open to clear a fault. And by the way, this line 1 is out of service right now. The last time the simulation was ran, it was left in that state. So that breaker 1 and breaker 2 are open. So that line's out of service, but there could be a fault at location 2 or location 3 here. And if that's the case, then one of those lines would have to open to clear the fault. So all these components I just talked about, the time breaker logic, the time fault logic, are all going to be modified to run the cases. I'm not going over the initialization of the load flow. That was covered in the virtual session on September 14th. But I do want to point out some things about the IBR. So this little box here is the IBR plant. I'm going to double click on that. Things that have to be changed. So remember, all the cases for the plant test were at 100 megawatts, and so this is 300 megawatts. So what do we have to do? This transformer has to be upsized manually to 300 MVA. If it's left at 100 MVA, there's too much voltage rise or drop, and the IBR plant is not going to work. The model is set up nicely so that we can do a lot of the changes just with editing parameters. So I'm going to right-click on the average plant model, and this first choice here is Edit Parameters. And the number of inverters, I need to change that from whatever it was before, and I think it was maybe 60, but I want 150. So 150 times 2.5. Actually, it was 50 before. Yeah, 50 before so times 2.5, so 125 MVA before. Now this is going to be 300 megawatts, but it's going to be like 325 or so MVA. So I need to change that. And also on the power plant controller, same thing here. I need to change that one, from 50 to 150. And this, I think, is everything. Nothing else has to change. You want to review Qmax and Qmin. We're not going to change that, but none of these parameters are really essential to change. Everything else is kind of parameterized inside the box, but you do have to change PREF because that's in megawatts. So we're going to change. I'll double click on that. The maximum value was 150 before, I believe, so I changed it to 300. All right, and then it's got to be. You need to adjust it in this slider thing here. Okay. So here is the study script that automates it. I don't want to leave that in the comment. It should say study script. So we'll take care of that. I have three lines to to manage here. So there's out of bus 14, there's one to bus 15, one to bus 4, and one bus 13. There's a timed fault logic by name, for each the line, the fault that's in the middle of each line. And then there's two time breaker logic components identified by name. The one nearest bus 14 I'm calling the local breaker. That's BRK 2, 4, or 6 time. The other one at the other end of the line is 1, 3, and 5. And then I'm also going to change the recorder, the ComTrade recorder file name. I did set up the ComTrade recorder. They don't need to record every channel, but I have each line can be in one of three states. It can be have a fault applied, and then the breaker's going to open to clear it, or it can have it can be out of service, where both breakers start open and stay open, or it's just going to be the line stays in service. It's not going to be faulted at all. So these are the different permutations or combinations that set the breaker and fault timing. This changes the recorder file name, and this is what loads the interfaces, out of those two tables. And then this logic here, I'm not going to describe it now, but read that as you get time. But basically, I want to, for each line to be faulted, I want to fault it with the other two in service, and then I want to take each of the other ones out one at a time. When I take one of those lines out, I have to put it back in service before running any more cases. And so that's what that logic does there. I will show you on the ComTrade recorder. Let's see, I should go up here. Yeah, the ComTrade recorder wasn't in the September 14th session, but since I want to run a bunch of these, 9 in particular, I put in a ComTrade recorder, but it's only taken 3 channels. We're not trying to debug the plant. Hopefully the plant model has been accepted and vetted and validated and attested to through running the plant tests suite on it. And so here in the system study, we're going to assume we only need the voltage, real and reactive power at the plant. There are synchronous machines and other elements in the system, so we want to looking at those as well. I'm not showing that here, but you of course want to look at other machine angles and see if any of them are losing stability. Doesn't appear to be the case in this simulation. When I run that study script, it's going to run those 9 simulations in sequence. And when I'm done, when that's finished, I can go to the Jupyter Notebook, cplot 7, and I'm going to just like I always load in the support functions to read the ComTrade file, enable matplotlib, and I already ran the simulations. They take, again, several minutes. But we're going to read ComTrade files out of the solar system case. And these are my cases. There's 9 of them. So the nomenclature here is the line to bus 13, that's where the fault is. X0 means no lines out of service. XL15 means the line to bus 15 is out of service before the fault. And here, XL4 means the line to bus 4 is out of service before the fault. So let's load those cases. And so it's loading 3 channels. Those smaller ComTrade files for that reason, but 3 channels from each 9 cases. And then I'm going to make the plot. And so you see there's some differences in the response, but they're all, the IBR recovers. And I didn't check all the machines, but it looks like, particularly the RMS voltage, it is oscillating a little bit, but it doesn't look like anything has lost synchronism. Of course, you'd want to look at all the other generators and verify that that's the case. But at first blush, it seems to be okay. So you would, in a real study, you would look at more conditions, but this is just to give you an idea of what can be done with automating a system study in PSCAD.